All right, ladies and gentlemen, today we're introducing chapter 7, which is called Alkynes. Alkynes have a c241, at least one. Okay. At least, okay. Slow start here. At least one c241. And what are we supposed to know already? What do we know already? Let's do a quick bond labeling. Oh yeah, nice spelling there. And geometry. So we got all these guys we're going to call A. And that's, what kind of bond is that? Is it a sigma or a pi? Sigma between what orbital on hydrogen every time? S on hydrogen. And the carbon has what hybridization with 4 sigma bonds and 0 lone pairs? sp3. So what's your, that's the answer. Sorry. Okay. And the geometry of atom A, since we're over here, atom A, because it's sp3 and it has 4 sigma bonds, what's the name of the geometry? Tetrahedral. What is the bond angles in a tetrahedral? 109.5 bond angles for any sp3 CC. All right, how about B over here? S from the hydrogen to an, careful, I heard a number that I shouldn't have heard. Why is it ST on the carbon? Because it has 1 sigma and a second sigma. Don't count these, they're both pi. Don't count pi for hybridization. No, no, no. Sigmas used to make hybrids, which are then used to make, hybrids are used to make the sigma bond. Okay, so that would tell us that atom B is the one that was SP. SP is what name of the geometry? Linear. And what is the angle of said geometry? 180. All right, and this is going to be your activity. You're just going to copy this. There's a question here. Why is A, quote, unquote, A weaker bond than B? So, yeah, copy the question and the answer, and that's going to be the whole activity. It's not a bad one today. Real easy. Easy for Jad to catch up. Yeah. Separate piece of paper, your own small, copy down just this activity 1 part. Everything I say in this box is what you're going to copy. Now we need to talk about electrons closer or further from the nucleus and why. That your answer must focus on those issues. So that issue. So in bond A, why are the electrons a little closer to carbon, further from carbon's nucleus than B, where the electrons are closer? Tell me why. So she's talking, I like the way she's talking. She said, in an sp hybrid, the percent S is 50%. So the electrons in the bond are closer to the nucleus than in an sp3 hybrid, an ASP hybrid, and sp hybrid. Doesn't sound good. Yeah. In a sp3, which is 25% S, 1 part S out of 4 parts. And I think that's a sufficient answer. Because S is closer to the nucleus than P. Higher percent S, closer to the nucleus than lower percent S. That's it. And I don't even think that's a new item. It was discussed previously, a long time ago. We're talking test 1. Didn't put it on test 1. So activity 1 is just the yellow box. You keep those with you. Yeah, make sure you get some pieces of paper ready. Okay, what else are we supposed to know? We're not finished. Let's do this carbon-carbon bonds. They're outside the yellow box. You don't have to put this on your activity. Bond C. How do you know it's a sigma? How do you know it's a sigma? There's only one bond. What's the hybridization of the carbon on the left? That's this one right here, sp3, and the carbon to the right, sp, which means this is also a label B, right? Label B, because it's linear. And that's C, and then we'll do D, and that'll be this sigma here. Oh, that's our best sigma of all, right? Both parts are 50% S. That's a good, strong sigma bond. Yeah. And what do we do at the end? We have dessert. What's for dessert? Always? She remembered my story about the student that saved nomenclature for the end of the test, and she said nomenclature. Yeah. Well, she saved it for dessert, but this one we're saving pie for dessert. Pies for dessert when we're doing bond types, right? And we do it at the end because they form at the end. So one of the pies, we'll call it E, and the other pie we'll call F, because they can't be the same orbitals making 2 different bonds. So you got to label, hey, it's the second bond, so you don't call it sigma. What do you call it? Pi. And the hybridizations are both, sorry, no, well, that's a bad statement. There's no hybridization in pi because pi is made from unhybridized. What's pi made from? You just got to do your Greek-English conversion and you're done. Greek-English conversion from pi to English. P orbitals make pi bonds. Nothing is easier to remember than that. P orbitals makes pi, and they have to match. So she said she wanted to use px. Now, in truth, to make her story true, you should be looking at the molecule, not like that, like that. It's okay. Molecules don't know which way you're looking at them, right? Because we drew our bonds in the x direction. That's all I'm trying to say. And when you draw your bonds in the x direction, that means you've already used the px hybrid, because that's the one that points in the x direction. All I'm saying is that was a wasted discussion. You can use px anytime you want. You can use py anytime you want. You can use pz anytime you want. You can't use px py. You can't use px pz. You can't use pz py. They have to match or they don't bond. They have to match or they don't overlap. If they don't overlap, it's not a bond. And we had a question back there.
You answered it.
Oh, it's my favorite kind of question, the one I already answered. Okay. And then F can't be the same as E, but it has to be a pi. You got to use orbitals that don't occupy the same location. So you pick py. Why not? Then we have all the bonds. And we did all the geometries. And what else are we supposed to know? Anything else we're supposed to know at this time? Yes, there's one thing we're supposed to know. Right there. pKa of a terminal alkyne. What? He didn't say that before. Terminal alkyne. It just means an alkyne at the end of a chain. Terminal, end. You don't have a pKa for any other kind of alkyne because the H must be attached to an sp hybridized carbon. If it's in the middle of a chain, there ain't no H on the sp carbon, right? For example, this does not have a pKa of 25 right here. This one right here does not have a pKa of 25 at all. pKa is 50. It's either, you know, you're picking either these or these. They're both alkane, right? That's an aside. And since it's an aside, and we had a terminal alkyne, give me a good name for an alkyne that's in the middle. It's within. It's not on the outside. Who studies medicine of the inside of your body? Internal medicine or internal medic studies that, right? It's an internal alkyne. Internal. Internal. Alkyne.
These two terms, terminal.
There's your two broad categories of alkyne. If you're an alkyne, you're either terminal and you have a pKa of 25, or you're internal and you don't have a pKa for the alkyne at all. Those numbers are not for alkyne, are they? They're for alkane because that's the kind of sp3 carbon they're attached to. All right. Then does that catch us up on all the stuff we need to know? From the past. New stuff, of course, new. Activity 2.
So terminal pKa of 25.
Yeah. Terminal has pKa of 25. Oh, I didn't write the pKa. Look at that. 2,5, thank you. Name both alkanes on this, alkynes on this page. And this is mostly review. And some of you can probably figure it out without any new information. You can tell me what to do if it was an alkene. It's a 3-carbon alkene, the first one, right? So we'll say this is molecule A, and now this is molecule B. And so this is activity 2. It'll be in a box when I'm done. A and B. So what 4 letters must you start with if you have a chain length of 3? Prop. And if it was a double bond, you would have ended it with ene. But this is not a double bond, it's a triple bond, so you end it with ine. And you're saying, don't I need a number? Don't I have to tell the teacher where the alkyne is? It has to be on the first. It can be 1 to 2 or 2 to 3. And if it's 2 to 3, it means you numbered it backwards because alkynes are more important than groups. So you only need numbers once you get past 3. And molecule B, we're past 3. Molecule B, I made a symmetrical one, so you can go left to right or right to left. Doesn't matter, right? 1, 2, 3, 4, 5, 6. So what are the 3 letters to start? Hex. Hex, careful. Ine. Couple ways to do this now. You got to tell me the ine is between 3 and 4. It's like saying the ene was between 3 and 4. 3 hexine or hex 3 ine. Yeah. And that is your yellow box number 2. We got short activities today. Why can't we do it like this all the time?
Professor, can it be in a cyclomolecule?
Oh, We had a question, can it be in a cyclomolecule? And he indeed has anticipated my next nomenclature. Okay, so
Because that's when things get messy.
no, nomenclature makes the world go round. You're saying nomenclature of cyclic things when things start getting messy. Okay. Well, we can do the student's favorite. Yeah. Dots. Yeah, we'll do one like that. Oh, triple bond. Yeah, I like it. And on this one, we'll do something like this. Yeah. Oh, no. I think that should be the second one. And on this one, I'm going to keep it first and second. I add another dot. Where's the biggest space? Another dot. So we don't have the same ring both times. There you go. And this one I'll go H. Yeah. So just in the box will be the activity 3 names. Nomenclature for C and D. Yeah. So we've got a situation where we got Enes and Ines, right? They have very similar priorities. They're like 1 and 1A. They're more important than any groups. Enes and Ines are more important than groups. So don't use as your decision-making process where those groups are. Your 2 choices for 1, 2, 3, 4, 5, 6 are these in both molecules. I'll go blue versus green, blue versus purple. You can number it going this direction, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Tell me why those are the only 2 possibilities based on this statement. Well, they both have an ene or an ine on one, and then the other one is on 4, right? Yeah, if you have the ene on 1, then the ine was on 4. If you have the ine on 1, then the ene was on 4. So really, there's if they're identical priority, then both these systems work. But I want to tell you, they're not quite identical. After I get some coffee. Sorry, I got a little energy bar in my throat. TMI. Okay. Enes have a higher priority by this much right here. Okay?
So we keep the E number 1.
Enes have a slightly higher priority because they can be E or Z because geometry. Can an alkyne ever be E or Z? It's linear. Answer no. So that makes it a little, it has less variability, so they view that as making it a little less important. It's a personal taste if you want to really break it down. But we got to go with their taste. So I want to have the ene on the lower number. Okay? So I think the baby blue wins, right? Based on that. And we'll make the baby blue win in this one too. Versus the purple inside. Okay, so baby blue for both. We'll do C here. And if you continued counting, I believe you get up to 9, 6, 7, 8, 9.
They're the same number.
They are the same numbers, that's right. 5, 6, 7, 8, 9. So cyclo, I like that. Cyclo, careful. Non. What's alphabetically first, ene or ein? Yeah, so ene first. And then ein. Baby blue says 1 ene, 4 ein. Okay, we're not done. We got groups and geometry.
On the 4.
On the, careful, baby blue.
Yeah, on the 2.
On the 2. It's one of those parenthesis groups. You haven't named an alkyne as a group ever.
That's what I'm waiting.
That's what he's waiting for. All right. Well, it's a 3-carbon group, correct? So it's a prop. Careful, it's got a triple bond in it. Prop 2 ein. And it's a group. It can't end with ein with an E. It's a group. What do all groups end with except for the halogen? YL. Prop 2 ein ill. I know it doesn't sound right. It sounds like you're ill. Yes.
Okay, but we said 2 just because we start counting.
Well, in a group, the carbon attached to the chain is number 1. When you're talking parentheses, inside the parentheses, the numbering is based on what number of the group. And carbon 1 is the one attached to the chain. So in this case, that's 1, that's a 2. So it's a prop 2 ein ill. It just looks messy. I want to tidy it up a little. 2 If you wrote propargyl, you'd get a big smile from me because that's a group. It's like allele is an alternate common name for squiggle CH2 triple bond after that.
The triple bond is on the first part.
Then it has no common name and it would be prop 1 einyl. Her question was if the triple bond was starting here and ending here, the name would be prop 1 einyl. Just like this with a 1. And there is no common name for that. So don't look for it. And we have a geometry on the double bond, and we got to follow the rules for that. We're cutting it in half. We'll use pink, the old cut. Don't forget to put the H on this. Oh, that's not an that's an octet violation. Now, both the 1 and the 2 are on this side, but I hope you realize this is the one that's closer to 9 than this one. So it's Z to 9. What do I mean by that? 9 is the 1, H is the 2. The 1s are on the same side. The 2 has to cross the 1 to get to the 1. It's just because you used this circle method that you had to compensate by drawing a weird geometry alkene, where this group's either inside the ring if you want it to be Z, or outside the ring if you wanted it to be E. Okay? And you just write Z. Okay? And since we're on that topic here and we have the right colored pen, the next one has a 1 and a 2 on the same side. That's not Z. And the 2 and the 1 are on opposite sides. You gotta go all the way over here for the 1. Yeah, that's E.
And why is the circle 2 and the Alkyne 1?
Why is the circle 2, this one?
Yeah.
Well, well, apparently Dr. Whitaker was going a little too fast for his own little brain. And he didn't realize that this triple bond was the same distance away as this triple bond, and this one doesn't have an H. I'm glad it came up now and not after I posted the video. Right? The 1 and the 2 are wrong. They both go CH2, C triple C. Do you agree? CH2, C triple C. But this one has CH at the end. This one has CC. CC is the winner. That's an easy fix, right? Tell me what to fix. Your 1 and your 2. And then the Z becomes E. Or double E here, huh? Yeah. Yeah, and that was the 2, 1. Yeah, the 2 and the 1 are close to each other. That means that's E. And over here, we like the baby blue. We already discussed the baby blue. So we got a group on carbon 1. You better use the parentheses. You don't have a common name for that group. It's a phenyl attached to another group. Do you agree? So when that's the situation, phenyl first, the thing attached to the ring last. And it's a propyl attached to the ring, isn't it? And what carbon number of the propyl has the phenyl? 3. 3 phenyl propyl. C6H5 is one of the ways to show phenyl. And I think I got this one to 10 carbons, didn't I? With blue, 7, 8, 9, 10. So this is a, oh, I forgot the C word. Cyclo. Dec. 1 ene again. Oh, technically that E shouldn't have belonged in the first one either. And then 5-ine. 5-ine. Now, if you do this on a test and you leave this E here, I'm not going to do a thing. I might just scribble it out. You will not lose any points. But it's not the end of a word. And just like in English, some words that they're not the end, you lose the E when you put it in the middle to make it an infix, as they say. And we had a question back there.
Instead of the 3, like the 3 phenyl and the propyl is basically no name. No, right?
No, this has nothing to do with cyclodec anything. This is the group only right here.
Yeah.
It's a propyl because there's 3 carbons attached to the chain.
Yeah.
And there's a phenyl on the third one.
But like if we add all the carbons together,
There's 9.
9. If we named it as a
No, there's thousands of groups with 9 carbons. There's no shortening of this name. You can't get it shorter than that. Okay, so what we got here is the end of activity 3. And we're going to start a new video on the next page.